This call is now being recorded.
So in last class we started with the chapter number 1, that is basics of heat transfer. So we discussed the introduction, and then we were discussing about the modes of heat transfer. That is, the first one was conduction, in which we have seen the basic law of heat conduction, that is the Fourier's law of heat conduction. That was given as Q equal to so we discussed for conduction, that is the basic law of heat conduction, that was Fourier's law of heat conduction. Plus Q dot is equal to minus K into A into dt upon Bx. This was the Fourier's law of heat conduction. So after that we discussed about one of the property that was thermal conductivity. So thermal conductivity tells about the material's ability to conduct heat. So we move to the second mode of heat transfer by the end of the class, that was convection. So convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion. So let us consider that there is a hot surface which is at temperature Ts, and let us consider a fluid is flowing over this hot surface with a velocity u infinity and temperature as T infinity. Now when there is no bulk fluid motion, in that case the heat transfer mode will be only due to conduction. So when a fluid flows over this hot surface, because of the fluid and surface interaction, one layer of the fluid sticks to the surface and attains a zero velocity because of the viscous effects. So if I draw the profile here, velocity profile, so u equal to 0 to u infinity. Okay. So as a consequence of fluid surface interaction, there is a development of region in the fluid through which velocity varies from 0 at the surface to finite value u infinity associated with the flow. Now the fluid is in direct contact with the solid surface here, sticks to the surface due to viscous effects, and there is a no slip, and this is termed to be as the no slip condition. No slip condition, where one of the fluid layer sticks to the surface and attains zero velocity. Now the layer that sticks to the surface slows down the adjacent layer because of the viscous forces between the fluid layers, and which also slows the next fluid layer and so on. Therefore, no slip condition is responsible for development of the velocity profile here, that is u as a function of y. This is your x direction. This is your So this viscous effect is responsible for the velocity profile here. Now the flow region adjacent to the wall, in which this viscous effects and thus the velocity gradients are significant, is termed to be as the hydrodynamic boundary layer. Hydrodynamic boundary layer. Now if we see here, the fluid property which is responsible for this no slip condition, and the formation of this hydrodynamic boundary layer is viscosity. Because of the viscous effect, there is a formation of hydrodynamic boundary layer and there is no slip condition. So viscosity is responsible for the formation of a hydrodynamic boundary layer. Now, if you see here, because of this no slip condition, one of the fluid layer is having zero velocity relative to the surface. So one of the implication of the no slip condition is that heat transfer from the solid surface to the fluid layer adjacent to the surface is by pure conduction, because there is no motion of this fluid layer. It is still here. So the heat transfer from the surface to this fluid layer, which is having a zero velocity, will be purely by conduction here, since the fluid layer adjacent is motionless. And this fluid layer attains the same temperature as the temperature of the surface, and this is termed to be as the no temperature jump condition. This is termed to be as no temperature jump condition. So if you draw a temperature profile here, okay, it will be so there will be a temperature profile which will be having a temperature Ts close to the surface and to T infinity where there is no existence of boundary layer. So there is a formation of a boundary layer where the temperature is varying. Are you all able to hear me here? Yeah. Okay.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay. Okay. Fine. So
But your screen is a little blurry.
yeah, that there is a light problem, and shadow of mobile is also coming. But when you will watch the video, it is very clear.
Sir, can you explain the no temperature jump condition again?
Yeah, I will explain now.
Yes, sir.
Yeah. So one of the fluid layer is now having zero velocity relative to the solid surface. Okay, because of the no slip condition. Now, since it is having zero velocity, there is no motion. So the heat transfer will be only purely due to conduction only. So since it is only due to conduction here, and it attains a same temperature as that of the surface. Okay, it will have the same temperature as that of the surface. So in that case, since this fluid layer is having the same temperature as that of the surface, then we can say this is a no temperature jump condition where the fluid layer, which is having a zero velocity with respect to the surface, has the same temperature. So it is termed as a no temperature jump condition. As you move forward in the y direction, your temperature is changing and it is reaching close to that of the fluid temperature, that was T infinity. So this is the no temperature jump condition where the fluid layer adjacent to the surface attains the same temperature as that of the surface. Sir, we cannot show temperature change profile by arrow vectors. Yeah, okay. Just for indication, I am showing here. So since there is only conduction in the fluid layer adjacent to the surface, I can write the value of the heat transfer, or I would write the amount of the heat flux which was convected away, heat flux, that is rate of heat transfer per unit area. So I can write the amount of the heat flux which was convected away from the surface here to the fluid layer adjacent to it is equal to the heat flux due to the conduction. And from Fourier's law of heat conduction, we are having it as minus of K. Now there is fluid layer, so thermal conductivity of the fluid into temperature gradient, that is T by dou y at y equal to 0. Since this is at y equal to 0, so minus k fluid temperature gradient at y equal to 0. Now, as a result of bulk fluid motion here, which is also termed to be as advection, the heat conducted into this layer is swept downstream and is eventually transferred to the fluid outside the boundary layer. So if I give you an example, that let us consider this is your one of the plate here and fluid is flowing over it, and let us consider one of the fluid layer sticks to the surface. I can show you some particles here. Let us consider this is the fluid layer which was adjacent to the surface, has zero velocity. Now if there is a fluid motion, you can see the particles were swept down from this surface and it was eventually transferred to the fluid which was flowing over it. So here what happened, there was a bulk fluid motion which convected the heat away from this fluid layer. So I can say the convection is equal to the sum of diffusion, that is the conduction in the fluid. From this fluid layer it will be also conducted to the adjacent layers also. So there will be diffusion, that is the conduction from the surface to the further fluid layers, plus advection, that is the bulk fluid motion. So diffusion, that means the conduction, advection, that means the bulk fluid motion. So convection can be said to be a two process involved, that is the diffusion plus advection. If there is no advection, then I would say the heat transfer is only due to conduction. It is not a convection process. Until unless both of these are a combination, we cannot say the heat transfer process is a convective process.
So could you please explain advection once more?
I'm not able to hear you. Can you please speak louder?
So could you please explain advection once more?
Advection, that means the bulk fluid motion. So the fluid has to be flow over, or the fluid has to be in motion over the surface. So when it is flowing over the surface, it is going to convect away, or it is going to say advect away. That means take away the heat which was conducted into the fluid layers here to the downstream or further away from the boundary layers which is being formed over the surface. That is the process of advection. So if there is no advection, only diffusion is there, then the process is not convection. It is a conduction process. If both are involved, then only I can say that the process is a convection process, or it is a convective heat transfer. Now convection can be classified into two sub-modes.
Sir, can you please explain the equation which you wrote? I didn't get the heat flux equation. Yeah.
Okay.
So
what I was saying, because of no slip condition, one of the fluid layers, because of viscous effects, is going to stick to the surface. Okay. So in that case, it will have a zero velocity. That means your advection term is not there. Only diffusion term will be there, since there is no motion and the heat will be conducted. Okay. So here, since the heat is only conducted, I can say in that case the convection process is equal to that of the conduction process. Whatever the heat will be conducted, that will be only convected away. So in that case, I can write the heat which was conducted to this fluid layer is equal to minus K fluid into temperature gradient at location y equal to 0.
okay, so this is only for the boundary layer.
Yeah, what?
So this is only for the boundary layer, right? That equation.
Yeah, there is a formation of the boundary layer at the surface here.
At
Okay.
this one. Okay.
At the surface here, this amount of heat will be available at the surface here. That only will be conducted further into the fluid layers, and when there is a bulk fluid motion or advection, this heat will be taken away downstream by the fluid here. Is this now clear?
Sir,
Ah, tell me.
am I audible?
Yeah, you are audible. Tell me.
Okay. So does conduction occur in the y direction, as in the heat is flowing upwards and advection is occurring in the x direction? Is that correct?
Advection is occurring in the x direction. The fluid is motion is there.
And the conduction takes place vertically, right?
Yeah, it is. It is all over this boundary layer condition. There is a fluid which is flowing here. It will be conducted into further fluid layers.
Okay. And how does this relate to the convection current that we have studied in
Yeah,
high school?
convection current involves
Yeah.
both this diffusion as well as advection. So the heat will be conducted into the fluid layers, and when there is a bulk fluid motion, this heat will be taken away from this fluid.
Okay, sir. Thank you.
Another question also, so sir, so advection involves heat transfer between adjacent fluid layers. No, when I'm talking about advection, it solely indicates the bulk fluid motion. It is not indicating the conduction process. So when I'm saying diffusion, it is already being conducted here to further fluid layers. So when there is a bulk fluid motion, it will take away the heat from this fluid layers downstream of the boundary layer. Shall we move forward now?
Sir,
Yeah.
you said that advection would occur to the downstream, that is.
Yeah. Away. See, when the wind is or the air is blowing over it, okay, it will be going in this direction. Okay.
Yes, sir.
So the fluid above this, it is going to get somewhat heated because of this heated surface.
Yes, sir. No,
Yeah.
actually, my question was that shouldn't the advection occur upstream because the fluid coming from the backside isn't heated and the fluid already which has flowed to the downstream
Yeah.
must have
So
been heated.
if you consider that there is a fan here, okay.
Yes, sir.
So the fluid, if you consider only one dimension right now, okay, not consider the three dimensions, only consider one dimension, that is this dimension,
Yeah.
okay, and the air is blowing in this direction. So it is going to take away the heat from here to the downstream here of this plate.
Uh, okay. So the heat transfer between the fluid layers would be, I mean, why can't it happen between the layer which we are talking about and the upstream layer?
Yeah, it is happening between this layer and the upstream layers here. It will be diffused to the further fluid layers here. And when the wind or the air is blowing over it, it is going to take away the heat from it.
No, sir, upstream as in to the left from where the flow is coming.
Okay, to the upstream, yeah.
So I
It
was
was
asking why.
upstream here also the fluid layer is in contact now. So when the fluid layer is in contact, it is having the same temperature as that of the surface here. Either you take at this side or this side, whole of this is at temperature Ts. So the fluid layer which is in contact with surface is at temperature Ts. And further to all the fluid layers, it is having the same temperature. These fluid layers, at if you are at say at certain location at Y, it is having a certain value of temperature. Okay, and when the fluid is coming, it is taking the heat away from it.
Okay, sir.
So another question is, so sir, so when heat is transferred through cooling pipes is through convection or conduction? So when you are considering a cooling pipe, okay, so there will be a convective heat transfer from the fluid to the inner wall of the pipe. So there will be a convection process from the fluid to the inner wall of the pipe. From the inner wall of the pipe to the outer wall of the pipe, there will be conduction. So when you are talking for a pipe, there will be two processes involved: convection from the fluid to the wall of the pipe and conduction through the wall of the pipe. Then, sir, so advection just changes the temperature gradient for conduction. Temperature gradient for conduction? I don't understand what you are asking here. Okay. If you have a problem, you can mail me. Name is Pranal Dev Singh. You can mail me. Okay. So let's move to the next topic. So convection is commonly classified into sub-modes. That is the forced convection. Convection can be either a forced convection or a free or natural convection. Free or natural convection. Okay. So when I am saying it is a forced convection, that means the fluid is forced to flow over the surface by some external means such as fan, pump, etc. Now when I talk about the free convection, the fluid motion is caused by buoyancy forces that are induced by density differences due to variation of temperature in fluid. So if I give you an example here, yeah. So if you see this slide, that is slide number 16. So there is a hot egg, okay, and it is having very high temperature of the outer surface. So let us consider that we are having a fan. We have placed a fan here. So it is blowing the wind over this hot egg. So you will find that it will take lesser amount of time for this hot egg to cool to the ambient temperature. While if you place a hot egg just in the environment, it will take a longer period of time here to cool here. Now, if you see here, we are placing a fan here. That means we are placing some external means to blow the air over the or the fluid over the hot surface. While here it is being exposed to the surroundings and there is no external means. So the process here, when there is some external means by fan or some pump, etc., if we are blowing the air over the hot surface, then it is said to be as a forced convection. If it is not there, then we call it as a free convection. So the free convection is generally caused because of the density differences due to variation of the temperature in the fluid. So the fluid layer which is close to this hot egg will have a higher temperature. The fluid adjacent to it will have a lower, and further fluid layers will have a lower temperature compared to the hot egg temperature. So here there will be a density differences, and because of it, the convection currents being set up, and there will be a process of free convection. So I hope you have understood the difference between the forced and free convection. Now, if you see here that since there is a higher fluid velocity involved in case of forced convection compared to the natural convection, I can say the heat transfer coefficient, I can say the heat transfer in forced convection is higher than transfer in forced convection is greater than heat transfer in free convection. Why? Because in case of forced convection, the fluid velocity is higher than the case for the free convection, and higher the fluid motion, more is the convective heat transfer. Right here, higher the fluid velocity, higher convective heat transfer. Now, as we had in case of conduction, a basic law, similarly in case of convection also we are having a basic law. So this basic law is termed to be as the Newton's law of cooling. Newton's law of cooling. So Newton's law of cooling states that the rate of heat transfer, that is Q dot, is equal to H into surface area into temperature difference between the surface temperature and that of the ambient temperature. So Newton's law of cooling states that the rate of heat transfer is directly proportional to the surface area from which the heat is being convected away, and it is also directly proportional to the temperature difference between the surface and the ambient temperature. And the constant of proportionality is H. So H here is termed to be as the heat transfer coefficient. H is known as heat transfer coefficient. Now, using this expression, that is the Newton's law of cooling, if I define H here, so H can be written as Q dot divided by surface area into Ts minus. So I can define heat transfer coefficient as the rate of heat transfer per unit surface area from which the heat is being convected away per unit temperature difference between the surface and the ambient temperature. And if I write the unit for this, so for rate of heat transfer, the unit is watt. For surface area, it is meter square. For temperature difference, it is Kelvin. So unit will be watt per meter square Kelvin. Now, important point here is that in case of conduction, we were having the area normal to the direction of heat transfer. Now here, AS indicates the surface area from which the heat is being convected away. AS is the surface area. Okay. Now let's talk about the resistance as we had in case of conduction. So from Ohm's law, we were having V equal to IR, R equal to V by, sorry, I equal to V by R here. I is equal to V by R here. So current is the effect, potential difference is the potential. Similarly for heat transfer.
Sir, in this case also we consider H to be constant throughout.
H indicates you
Heat
the
transfer.
amount of the heat which was being convected away. Okay. Now we will see later on how the temperature is going to affect it, but we have to consider the H to be constant. Okay. H indicates how much amount of, it gives an idea about how much amount of the heat which is being convected away from the surface. So H is, for any process, I would say H is a constant quantity. I hope
Okay,
it is
thank you,
clear.
sir.
Huh?
Okay, sir. Thank you, sir.
So rate of heat transfer is the effect, and temperature difference is the potential, right? Sorry. By, I can say, thermal resistance to the convection. Now from this relation, that is heat transfer would be the effect here. I can write Q dot from Newton's law of cooling as H into AS into Ts minus T infinity. So I can write this Q dot is equal to, this would be the temperature difference, so delta T upon 1 upon HAS. So if you compare these two relations, so I can write the convective resistance is equal to 1 upon HAS. This is the convective resistance to the heat transfer. Okay. Use the slides here. So the heat transfer coefficient depends on variables such as surface geometry, that is the surface area, then the nature of fluid motion, so that is it might be a laminar flow or a turbulent flow, then properties of the fluid, that is its viscosity, density, etc., and the fluid velocity. Higher the fluid velocity, higher would be the convective heat transfer. So the values for the convection heat transfer in some of the processes, that is the gases, it is very less. It ranges from 2 to 25 watt per meter square degree centigrade. Then the convection of liquids, it is higher than that of the gases. It ranges from 10 to 1000 watt per meter square degree centigrade. So forced convection is having a higher value of heat transfer coefficient compared to free convection. So you can see it's having just 10 times, that is 25 to 250 watt per meter square degree centigrade. Forced convection of liquid is higher. So it is having 50 to 20,000 watt per meter square degree centigrade. Also, boiling and condensation is also a convective phenomena. So it is having very high value of heat transfer coefficient involved, ranging from 2,500 to 1 lakh watt per meter square degree centigrade. Now coming to the third mode of heat transfer, that is radiation. So radiation is the energy emitted by the matter in the form of electromagnetic waves as a result of the changes in the electronic configurations of the atoms or the molecules. So unlike conduction and convection, radiation does not require any intervening medium. So conduction requires a medium, same as convection. So someone is writing in the chat box here. Yeah, Newton's laws doesn't take in consideration the dependence of heat transfer on fluid velocity. Yeah, it takes, no. It obviously it takes, because higher would be the value for the velocity, higher would be the convective heat transfer. So in the Newton's law of cooling, if the value of heat transfer is going to be high, so in that case your H is going to be also high. So next is H average out value for a specific process. So if you are having a higher velocity, in that case you will have a certain value for H. If you are increasing the value for velocity, your H is also going to change. So these two processes, conduction and convection, both involves a medium. But radiation doesn't require a medium. This does not require medium. Now in heat transfer studies, we are interested with thermal radiation, that is radiation which is due to the temperature. So we are going to discuss only here about the thermal radiation. That is the radiation due to the temperature. So now, as we had in case of convection and the conduction also, a basic law. So there is a basic law for radiation also, and it is termed to be as the Stephen-Boltzmann law. Stephen-Boltzmann. And it states that your black body emission power, or the emission power here, is proportional to T to the power 4, and it is equal to sigma T to the power 4, where constant of proportionality, that is sigma, is the Stephen-Boltzmann constant. Sigma is Stephen-Boltzmann constant, and its value is 5.67 10 to the power minus 8 watt per meter square. So the Stephen-Boltzmann law states that the emissive power or the emissive flux, I would say, this is emissive flux, is directly proportional to fourth power of the temperature. Now here the temperature is in Kelvin. Always remember that using this formula, temperature is in Kelvin. So I can write this emissive power is equal to sigma into T to power 4. So this is the emissive flux. So you can multiply area here. So EB can be written as sigma into A into T to power 4. Now, the idealized surface that emits radiation at this maximum rate is called a black body. Black body. So the body which emits radiation at this maximum rate is termed to be as a black body, and this EB is written to be as the black body emissive power. Black body emissive power. So for a real surface, we have the definition of the emissive power as equal to epsilon into sigma into T to power 4. So epsilon here is known as emissivity. So is emissivity of a surface. This is of a surface.
Excuse me,
And
sir.
yeah.
Is EB the emissive flux or the emissive power?
It is said to be as emissive power also, or you can say it to be emissive flux, because this is the emissive, it is indicates the rate of heat transfer due to radiation per unit area. So
Exactly.
you can write
EB
as,
and
yeah,
the EB that you just pointed to, that was the power per unit area, right?
yeah.
So
Actually, it is rate of heat transfer by the radiation per unit area. So it is indicated here as emissive power.
okay,
Yeah, I
thank you,
understood
sir.
your point. So I referred to that word, that is emissive flux. But when we
Okay,
talk
so
about, when we write for radiation, we generally said to say it to be as a emissive power
when we take power, we'll need to multiply area to
by
the
area.
RHS,
Yeah,
right?
you can, if you are writing the about the amount of the heat transfer by radiation, you can multiply it by area here.
Okay, thank you, sir.
So this is indicating your emissive flux here. This is per unit area. Okay, so I was saying the emissivity of a surface depends upon the surface material and finish. Now, this emissivity lies between 0 to 1. Now, if there is a so if there is a if there is a body here, and let us consider its temperature is Ts. Temperature is Ts. Its surface area is As, and the surface is having an emissivity value as epsilon. Okay, and there is a surrounding air at a temperature T surrounding. Okay, so some amount of this radiation can be incident to the surface, and there would be some amount of the radiation being emitted from the surface. So any body which is at a given temperature emits radiation. So I can write here that is the amount of the radiation heat transfer, that is Q radiation, is equal to, that is the emissive emissivity here, epsilon into sigma into surface area As into Ts to the power 4 minus T surrounding to the power. So this is known as the basic law of radiation, which is going to govern the radiation. The basic law is said to be as the Stefan-Boltzmann law. So for any body which is at temperature Ts, which is exposed to surrounding, I can write the value for the radiation heat transfer in this form. Now, similarly, as we had in case for the convection and conduction, if you want to determine the thermal resistance for this, so you can have Q radiation is equal to temperature difference by thermal resistance for the radiation.
So the emissivity of the surrounding will be different from the surface, right?
So you are saying, do we define emissivity only for a black body or for any body? For emissivity for a black body will have the emissivity value as 1. Epsilon is equal to 1 for black body. And for a real surface, this emissivity is going to be less than 1. So for a real surface, you have to multiply this epsilon value to this value for real surface. This is for real surface. So emissivity will be of the surface from which this radiation heat transfer is going to occur. This is Q radiation. Okay. Now it is clear.
So for the heat transfer from the surroundings to the body, the emissivity of the surrounding will be different, right?
So surrounding acts since the temperature of the surrounding is constant at T surrounding, so we can consider it to be as a black body. So epsilon will be equal to 1 for it.
Okay,
Emissivity is defined for the surface. It is clear now?
Yes, sir.
Okay. So you can write Q radiation is equal to delta T by thermal resistance for the radiation. So if you compare these two expressions, you can have the expression as it is given in the slide also here. That is RTH for the radiation is equal to 1 upon epsilon into sigma into AS into TS plus T surrounding into TS square plus T surrounding. This would be the value for your thermal resistance for the radiation. So radiation is a volumetric phenomena, and all solids, liquid, gases emits and absorb and transmit radiation to varying degrees. Now it is a surface phenomena for opaque solids. Now there are other properties also involved in phenomena of radiation. So let us consider that there is a surface, okay, and say some amount of radiation is being incident to it. As radiation, it is being incident to it. Okay, some amount can be absorbed into the surface as Q absorbed, and some amount will be reflected from the surface. Now the amount of the radiation energy which is incident to any surface is said to be as irradiation, and it is denoted by G. Irradiation is the radiation energy per unit area. So this is a flux. G is the flux. Okay, that is for per unit area, surface area to which the radiation energy is being incident. Now this Q absorbed is a part of this incident radiation which is incident to the surface here. So here we define one property that is known as absorptivity. That is given, this energy is given as alpha, that is absorptivity into Q radiation which is incident. So this is incident. So Q radiation which is incident. And you can have Q reflected as 1 minus alpha into Q radiation which was incident. So here we define this property absorptivity as alpha equal to, that is absorptivity as Q absorbed by Q incident radiation. Okay. So similar to this emissivity, this alpha also ranges from 0 to 1. Now black body is perfect emitter and perfect absorber. So emissivity is equal to 1 for black body, same as this absorptivity will be also equal to 1 for black body. So alpha depends upon the wavelength of this irradiation and the surface finish of the surface. So we will read further more properties which are related to radiation in the radiation chapter, and we will have a detailed study at the end of the course. We will have a detailed study or a detailed chapter for this radiation. So we will discuss in detail at that time for the radiation. Now we will move forward here to the next topic, that is the first law of thermodynamics. Now this subject, heat transfer, is just an extension of the thermodynamics. So if we talk about the first law of thermodynamics, that is conservation of energy. So if we consider any system here, so I can write from the conservation of energy, that is whatever the energy which is entering into the system or which is leaving the system can give us idea about how much energy was stored by the system or what is the change in the energy of the system. So let us consider that there is a system. We are having a system here. This is the control surface. Okay. And since it is interacting with the surrounding or any other system or any surrounding here, so there will be some energy which is entering into the system. Some energy might be leaving the system. It might be heat or it might be work. So there will be some amount of E in, some amount will be E out. So I can say the total energy entering the system minus the total energy leaving the system will indicate the change in the energy of the system here. So I can write from here, that is E in minus E out is equal to delta E of the system. So if I write in the rate form, it can be written as E in dot minus E out dot is equal to dE system upon dt. Now if it is a steady state, that means the values are not changing with respect to time. So at that point, this dE system upon dt, this time derivative will be cancelled out. So in that case, I can have E in minus E out is equal to 0, or E in, that is whatever the energy which was entering the system, is equal to the energy leaving the system. Now there can be some processes which can occur within the system. For example, let us consider that if you are having a heater placed in a room, okay, there will be a change of electrical energy into thermal energy, and you will find the temperature of the room is changing there. You can consider the room as a system there, which is interacting with the outside surroundings, and if you are having a heater within your room, it is going to change the temperature of your room, where the electrical energy will be changing into thermal energy, and the heat will be given out by the heater, and the temperature of the room will be changing. So here there will be a heat which will be generated into the system. Or you might take an example of a chemical reaction, exothermic chemical reaction. So it will also give up some amount of heat. So if there is, or if some thermal energy may be created within the control volume due to conversion from some other energy forms, is referred to be as the heat generation. That is termed to be as the heat generation because of the conversion of any energy form to the thermal energy. That is termed to be as the heat generation term. So if there is a heat generation term, I can write this equation here as E in plus the energy which was being generated within the system here minus E out is equal to d system upon dt. So this is known as the application of the first law or the conservation of energy to the heat transfer analysis. And this will be applicable to all the heat transfer problems which we are going to discuss in this course. So this is the basic equation which we are going to apply for the analysis of all the heat transfer problems for the getting the solutions. Now, if we talk about this surface here, let us consider that there is a surface. Okay, and let us consider some amount of the heat is being conducted into this surface, that is given as conductive heat flux is being conducted into this surface, into this medium from high temperature side to low temperature side. Okay, and if you consider this to be your control surface here. Now surface does not have any volume, so it cannot store any energy. So, and let us consider some air is blowing over this surface here at temperature T infinity and velocity U infinity. So what mode of heat transfer will be at the surface here? It will be a convection from the surface to the ambient air here. So there will be a convection heat transfer. I can denote it by flux, convective heat flux from the surface to this ambient air. Conduction throughout the medium or a wall, convection from the surface to the ambient air. Now, if you consider that there is T surrounding, that is the surrounding temperature, there can be a radiation heat transfer from the surface to the surrounding temperature, and you can have Q the radiation. So I am writing in form of heat flux, so heat flux for the radiation. So if you apply the basic law, that is the first law of thermodynamics here, energy balance here, I can say E in minus E out plus energy generated is equal to change in the energy of the system. Now, if I say that this is a steady state, so this term will be cancelled out. If I say there is no heat generation involved here, so energy generation term is cancelled out, and I can write E in minus E out is equal to 0. Now, what is the E in here into this surface? That is the conductive heat flux. So I can write for E in, that is the conductive heat flux. Now, if I see what is the E out here, it is the convective heat transfer and the radiative heat transfer here. So I can write it as minus for the convection minus for the radiation is equal to 0. So this is the surface energy. Using the surface energy balance, I can write in this form, and I can then write the basic laws for the conduction, convection and radiation, and then I can solve the problem for either the surface temperature or for any other term. So this was the theory related to the chapter 1, that is the basic of heat transfer. Now we are having some problems related to this. So the problem number 1 here is given as that there are hot combustion gases of a furnace which are separated from the ambient air and its surrounding, which are at 25 degrees centigrade. So here it is given that your T infinity is equal to T surrounding as 25 degrees centigrade by a brick ball which is 0.15 meter thick The brick thermal conductivity is given as 1.2 watt per meter Kelvin, and the surface emissivity is given as 0.8. Now, under steady state conditions, the outer surface temperature is 100 degrees centigrade, and the free convection heat transfer to the air adjoining the surface is given by this H equal to 20 watt per meter square Kelvin. Now it is asking what will be the brick inner surface temperature. So if I draw for a brick here, which is 0.15 meter thick, and it is having a thermal conductivity of 1.2 watt per meter Kelvin. Is there anyone having class now?
We already have a lot of classes today.
Okay.
We'll try we'll try this question and we can discuss next time.
Yeah, okay. So you please try the problem number 1 and 2 given in your PPT. Okay, problem number 1 and 2, and then we will discuss this in the next class. So tomorrow is a holiday. So can we have tomorrow an extra class, or shall we have this in next class only? Next class, okay. Okay, fine. We will have it in next class. So tomorrow is a holiday, so we will not have the class tomorrow. Okay, fine. So I stop the class at this point. So please try to solve these problems given in your PPT. Yeah.
Excuse me, sir.
No, please tell me.
Sir, how is Q conduction equal to E in?
See, I have shown you in that. Yeah. Here you are asking?
Yes, sir.
So what I am doing here, I am considering this surface here. Okay. I am considering this is your surface through which all this process is occurring. So to this surface, the heat will be conducted. If you are considering this at temperature T1, surface here is at temperature
Okay,
T2.
sir. Okay, sir. Got it.
Got it?
Got it, sir. Yeah. I thought we were talking about the body.
No. Here there will be a heat transfer from high temperature to low temperature. So at the surface, the analysis was done.
Yeah. Okay. Thank you, sir.
Okay. So at this point, I'll stop the class. So in next class, that is on Tuesday, we will discuss further. We will discuss the problems also, and we will discuss application that is for microwave oven. You can see at the last we are having a discussion for microwave oven. So we will do that. Okay. Thank you, class.
Sir?
Yeah. Excellent.
If possible, can you please go back one page to the Q radiation formula which you had written?
This one?
No, above it.
Okay. This one you are saying?
Yes, sir. So in this, I asked, you said the T surrounding can be taken as a black body.
Yeah, since
because
the atmosphere here is having temperature T surrounding as constant. Okay, whatever you do,
right,
temperature of the surrounding. If you place a heated body here, this temperature of the surrounding is not going to change.
Will not change.
It's constant. So generally, the surroundings is taken to be as a black body.
So, sir, then shouldn't the epsilon be inside the bracket, like epsilon Ts raised to 4? Unless it is for a pair of bodies.
In this formula you are saying?
Yeah, this one. So if surrounding is taken as a black body and epsilon is only for one surface and not a pair of surfaces, then it should be epsilon T raised to Ts raised to 4 minus T surrounding raised to 4, right? Because by placing epsilon outside, you mean that even the T surrounding radiation will be reduced.
Yeah, just to consider for a general case, I am saying that if there is a surrounding or if there is any body which is being maintained at T surrounding, so accordingly I have written it here in this form. taking the emissivity as epsilon for the surface. So if you are considering that there is a enclosure, so in the enclosure, if you are considering the surface is having a emissivity as epsilon, you can write in this form. So we will discuss this in detail in the radiation chapter. I will show you how we will get this.
Okay, sir.
Sir, is there any relation between epsilon and the alpha? The epsilon in this Stephen Boltzmann law and in the next of the irradiation.
You are saying about this one?
Yes, sir.
So according to Kirchhoff's law, your epsilon is equal to alpha. Yeah.
Okay, sir. So epsilon also depends on upon the color of the body and the surface finish.
It depends upon the surface finish. Yeah, obviously, if you place white color over the surface, its emissivity is going to change.
Okay, sir.
White
Thank you,
paint. If you place a white paint over the surface, its emissivity of the surface is going to change. Correctly.
So, sir, we have any body like whose absorptivity, the alpha absorptivity is 0. Okay. Thank you, sir.
Absorptivity is 0.
Yes, sir.
Yeah, that same example. If you apply a white paint, it is very close to 0.
So it's not perfectly reflective surfaces, no, but it will absorb some of it, no?
Yeah.
Like we can't have alpha equal to 1. Sorry, alpha equal to 0.
I'm saying that means
I mean alpha
absorbing
equals
all the
0.
radiation. So that is a characteristic of a black body.
Yes, sir. Alpha equals 0, as he is saying that it will reflect all of it. For white body also, it will absorb some of the heat, no?
Yeah, it will absorb some of the heat. You cannot say it will be equal to 0. It is difficult to have value as 0.
Yes, sir.
But if you apply some paint or something like that, and then it might be very small. But exactly 0, that is not possible.
Okay, sir.